So we are done with the transistor, right? Our goal is now I have the transistor. Then how is it going to operate in my circuit? Before that, I want to clarify a concept we sometimes even myself overlook until many years after graduation. When we talk about analog, we talk about small signal. What exactly it is? So here is the picture that I want to show. I have a VGS, for example, I bias the gate. What does it mean? I actually may bias it at 1 volt. I need to have a 1 volt. And then I apply some signal to it. This signal may be 10 millivolt peak, right? So what is the value of the real signal? This point is going to 1.01 volt. This point is going to be 0.99 volt. Your transistor actually see you applying a signal oscillating between 0.99 to 0.10 volt. That is the real situation, okay? But then we say, well, the total signal may be the total, I don't know how to call it, it can be confusing. Total VG is equal to maybe the DC plus the small signal, right? So this is 1 volt and this is plus minus 10 millivolt, right? And then you get 1.01 volt, for example, right? Your transistor really see this overall voltage, but this voltage is actually a constant voltage plus a small fluctuation on top of it. And this is the small signal we will be talking about in this class. Similarly, when I apply this VGS to this transistor or this circuit, it changed the current, it changed many things. But exactly what's going on? Well, this transistor was biased maybe at 1 milliampere. When you apply this small voltage, the current starts changing and fluctuating maybe by, let's say, 10 microampere. So your current actually changed from maybe 1.01 milliampere to 0.99 milliampere. Okay, so when we say that we have a negative AC signal, for example, negative 10 microampere, it doesn't mean that your transistor is conducting negative current. All the current still go from the drain to the source. It's just that you have less current, as if you have a negative small signal going from source to drain. Is this okay? This is very important. This is a very important concept. So when we are doing so-called small signal analysis, our goal is this. You need to DC bias the circuit. Do not think that I just want to apply 50 millivolt to the gate and I hope that it will amplify. Then you will come into contradiction. What isn't that the gate voltage needs to be larger than the threshold voltage, which is 1 volt? How come 50 millivolt? No, it doesn't, because we bias it with the DC already, maybe 1.2 volt, and then you apply 50 millivolt, okay? So you solve the DC bias circuit. You need to solve it. You need to understand what it is. And once you solve it, you will do something you call, you're going to extract the small signal parameter, right? And you know this already. For example, GM, R0, right? We will explain more, right? So under this DC bias condition, what is the strength of the transistor in different aspects? And then based on that, you solve the circuit to find, for example, input impedance of the circuit, output impedance of the circuit, transconductance, gain, bandwidth, etc. Okay, so that is the main point I want you to be aware of. Is this okay? Let's look at a simulation as an example. I hope that this one will work. Right? For example, here I have a circuit. What am I doing? I have a sine wave. The input amplitude is 1, but this is just because not really 1, right? It's just 1 unit, what it means. If you look at this one, do you see that I DC offset it to 1 ampere? I'm a 1 volt, right? So what exactly it is doing is that it has 1 volt and it has an amplitude with 10 millivolts about it. And this is connected to this transistor common source you will learn later. And let's just run it. If I try to probe the input, do you see that I do have a small signal, but it oscillates about 1 volt. That is what it is doing, right? But when we do small signal analysis, we will say, oh, my input signal is 10 millivolt. But in reality, it is 10 millivolt added to the top of the DC bias. How about the current? Yeah, this is voltage, right? So we need to look at the right and look at the red one, right? Look at the right. Again, it already has some current, maybe about 10 microampere. When I apply this, maybe I remove the 2 here, right? When I apply this green, oh, you cannot see it. Okay, now you need to teach me. Hammer?
To do this in lab if you can't do it.
Because I don't grade the lab, that's why.
We should change the lab requirement.
Color scheme. No, let me tell you why. I'm giving you a real world situation. Your VP, how do it? This one?
It's fine.
Okay. Okay, thank you. Yeah? Okay, I think it's about the, okay, I don't want to embarrass myself more. So, but this is real life. Your VP doesn't know how to do it, but he will ask you to do it in your presentation. Okay. And you cannot say anything. Yeah, thank you. Okay, so you see that for this green one, right? It is the input. Actually, yeah, it's the input voltage. And what does it do? It actually changes the bias current, right? And later, you need to actually extract this fluctuation as your output, right? And we can do one more. This is the current, but maybe you are interested in knowing what is the voltage. Then you get the blue one. So you see that this blue one, for blue one, you also look at the left, right? It has a larger amplitude. And the result of this is because the change of the current times this resistor give you this larger amplitude, right? And then you get a gain of this amplifier. Of course, you know how to do it. We will analyze again later. But just want to make sure that you see everything is way above 0 when we're doing this analysis. Okay? Any questions? Now, so if you're okay, that's good. Then let's go to the next page, right? So